Hi and welcome to another lesson in abstract algebra. In this lesson, we will be covering the orbit stabilizer theorem and its relation to the symmetries of the so-called Platonic solids. Okay, so to begin, let me define what we mean by a g-orbit and the stabilizer of an element. So here, you have a non-empty set X and you have a group of permutations on X. So parang you can imagine that X has elements in it. You can consider all the permutations on X, right? Maraming paraan to permute X. In fact, if X is finite with n elements, merong n factorial na permutations na pwede. So here, we did not consider all the permutation. We just need a subgroup. In other words, I just need a group not necessarily containing all the permutation, no? That permutes the elements of X. Parang imaginein mo, si X ay parang isang lugar, no, na may mga points. Si G ay mga permutations or mga functions that rearranges these things. Pag may isang element ka sa G, in-apply mo sa X, magkakagulo yung mga elements ng X. Or parang you can, sa language ng mga mathematicians, G acts on the set X. So mag-fix ngayon tayo ng isang element X from capital X. Meron tayong tinatawag na G-orbit of X. Ang laman ng G-orbit of X is the set of all images pi of X where pi is in G. Ang gagawin mo, lahat nung nasa G, i-apply mo sa particular point na X na yun. Parang ito yung X. Medyo lalakihan ko. Alright, si X. Ito yung little x, no? Ang gagawin ko, ito kuwari si G. Si G meron tayong mga permutations dyan, ganyan. Ang gagawin ko ngayon, kunwari, i-apply ko yung pi 1 of sa x. Mamove siya dito, no? Apply ko yung pi 2 of x. Apply ko yung, and so on, hanggang pi n of x. Lahat ng mga pinuntahan ng x, including itself, kasi yung identity nandito eh. Ang tawag dun, G of X, G orbit of X. Kaya kung mapapansin nyo, ito yung nasa loob ng X. On the other hand, kapag sinabi natin stabilizer of X in G, is denoted by this symbol. Ang laman naman nito, ito naman lahat ng mga permutations dun sa X na nandun sa G, na mag-stabilize sa X. When you say stabilize, yung hindi gagalawin si X sa lugar niya. Kasi posibleng may mga permutations that doesn't move a particular element. Magbibigay ko example. Halimbawa, yung permutation na ito, 2, 1, 3, 5, 4. This permutation in S of 5, ang X mo dito, 1, 2, 3, 4, 5. Yung permutation pi na ito, ini-stabilize niya ang 3. No, 3 goes to 3 and it moves everything else. Kaya yung pi na yan ay nandun sa stabilizer nung element na 3. Hinahanap mo kung sino-sino yung mga permutation that fixes 3 in its place, or in this case that fixes x in its case in its place. So just like what I mentioned already, yung G orbit nasa loob ng x is stabilizer nasa loob ng G. Nasa magkaibang lugar yan. May relasyon ba or magkapares na level ba yung X at G as sets? No, kasi ang laman ng X, mga points, na pine-permute ng mga elements ng G. Medyo weird, no? Pero ganun. It turned out that G, the stabilizer, is not just a subset of G. It's indeed a subgroup of G. To see why, no? Una sa lahat, yung identity function, of course, fixes X. So, the identity function on X is in the stabilizer of X. If you have two permutations that stabilize X, their product will also stabilize X. Pi 2 stabilizes X, so X lang to. Pi 1 also stabilizes X, so X lang ito as a final output. In other words, the product pi 1 times pi 2, composition yan ha, also stabilize x. Correct. So, si pi 1, pi 2 nandun sa stabilizer ni x. If pi is in the stabilizer of x, then pi of x equals x. Apply mo yung pi inverse on both sides, ma-undo yung pi, magiging x na lang, pi inverse of x. That implies that pi inverse also stabilizes x. Hence, G is a subgroup. Example, let x containing 1, 2, 3, 4 be the set of vertices of a square. Let R be the permutation 1, 2, 3, 4, the cycle 1, 2, 3, 4, and S be the transposition 2, 4. Let's take the group G to be the subgroup generated by R and S. So, gagawin ko, magdodrawing ako dito ng square. No? Kita nyo yung square dito. Yan yung 1, 2, 3, 4. You can think about R. No? Dahil itong cycle na to, it makes 1, it transforms 1 to 2, 2 to 3, 3 to 4, 4 to 1. So, pwede nyo isipin na ito yung rotation at an angle of 90 degrees. On the other hand, yung transposition na 2, 4, it fixes 1 and 3, and it interchanges 2 and 4, so it's a mirror reflection about this axis. So, alam natin na itong dalawang elements na to will generate a group isomorphic to D4. Ito yung 8 elements niya, no? Ito yung 4 na rotations, ito yung 4 na mirror reflections. In fact, I think ito yung axis ni, tingnan natin yung R, for example, RS. Anong product RS? Ano yung RS? Yung RS, 1, 2, 3, 4, 2, 4. Tingnan natin kung anong product na ito. C1, saan dadalhin? 1, fix here. 1 goes to 2, so 1 will go to 2. Where will 2 go? 2 to 4, 4 to 1. So 2 goes back to 1. Eh si 3, saan pupunta? 3 is fix 3 to 4. Okay? Then where will 4 go? 4 to 2, 2 to 3, 4 back to 3. O, tapos na. So, si RS, if i-interchange si 1 and 2, interchange si 3 at 4, paano yun? Ito, bale, yung axis nung RS. Papalit si 1, 2, papalit si 3, 4. Okay. Using the same computation, you can check that this is R squared S. Ito yung axis ni R squared S. Ito naman yung axis ni R cubed S. Si R squared, 90 degree rotation, 180 degree rotation. Si R cubed, 270 degrees rotation. Okay? Ano ba yung orbit, G-orbit ni 1? When I say G-orbit, pag in-apply ko, isa-isa, lahat ito, sa 1, saan pupunta si 1? Ano yung mga pupuntahan ni 1 ng mga vertices? Diba, if I apply ID on 1, si 1 nandyan, di ba? Tama? Si R, pag nirotate ko yung square ng 90 degrees, saan pupunta si 1? Pupunta siya sa 4. So, si 4 nandito. Eh, si R squared, pupunta siya dito. Si R cube, pupunta si 1 doon sa 2. Kaya actually, lahat pupuntahan niya. Kaya nga ang G-orbit niya ay si X. Okay? Ano naman laman ng stabilizer ni 1? Sino-sino mga permutations dito, right, ang mag-stabilize sa 1 sa lugar niya? Siyempre, nandun na yung identity. Di ba? What else? Si S. Di ba? Si S will stabilize 1. It will fix 1 in its place. Are there any other permutations here that fixes 1 in its place? You will find that no other permutations will fix 1 in its place aside from the identity and S. So there are basically 2 elements in this stabilizer. Subgroup yan. In fact, this is a subgroup generated by S. Ano ba si 2? Ang G-orbit niyan, X ulit. Lahat kaya niyang puntahan by applying any of these, all of these. Tapos, mga permutations naman nag-stabilize ito sa identity, tsaka sino kaya itong axis na to? Yun yung r squared x. Tama ba? R squared s ba yan? Yes. No? Naalala niyo yung drawing ko kanina. Yeah. So, yun na. Tingnan nyo to. Ilan laman ng g-orbit ng elements? 4. Ilan laman ng stabilizer niya? 2. 4 times 2, 8. Nagkataon kaya yun? Hindi. Actually, it's a theorem. And that is what we call as the orbit stabilizer theorem. It says that if X is a non-empty finite set, and G is a subgroup of S sub X, or G permutes the elements of X, and if you take a point X in the set, then the order of the group equals the number of elements in the G orbit times the number of elements in the stabilizer. To do the proof, no, ganda lang yan. So, mag-fix nga tayo ng isang point in the set X. For simplicity of notation, let's call by the symbol H the stabilizer of the element X in G. Then, of course, sabi nung nakaraang remark, si H ay subgroup ng G, and hence, the Lagrange theorem applies. Dapat yung order ni H dinidivide yung order ng G. Tama? In fact, the order of H times K equals the order of G, where K is the number of left cosets of H in G. Naalala niyo to? Ito yung sa proof ng Lagrange theorem. Thus, to finish the proof, ito kasi yung stabilizer, di ba? Para matapos yung proof, kailangan ko lang ipakita na yung K, yun yung number of elements in the G orbit. But remember, K represents the number of left cosets. So we just need to show that the number of left cosets in H equals the number of elements in the G orbit. In other words, we do not count, no? In math, when you want to show that two sets have the same number of elements, we normally exhibit a bijection between these sets. So we show that there exists a bijection between the set of left cosets of H and the G orbit of X. Tawagin natin big lambda or capital lambda, the set of left cosets of H in G. So, ito yun. Mga left cosets ng H. Magde-define ako ngayon ng function which is our candidate for the bijection. I'll call it phi to be the map from lambda to the G orbit. The function will send the left coset pi H to, gagawin ko dahil yung pi ay nasa G, i-apply ko siya sa X. Pag in-apply ko siya sa X, corresponding din, nandun ka sa G orbit ng X. Now, meron tayong a little problem in this definition. Kasi remember that two cosets can be equal kahit na magkaiba sila ng representative. And the definition of it depends on which element representative represents the cosets. Paano kung halimbawa kasi, let's say I have pi H, pare siya kunwari sa, let's say, rho H. So, kung ganun, kung i-apply ko si phi sa pi H, ang lalabas, diba? Pi of X. Pag i-apply ko naman si phi sa rho H, na parehas lang naman din sa pi of H, magiging rho of X. Baka ang mangyari, dahil magkaibang permutation si pi at 0, parehas kaya ito? Kasi kung hindi, problema yung definition na yan, no? In other words, we wanted to show that this mapping is well-defined. Paano yun? Ganito. Kunwari si pi 1 of pi 1h can be represented in another way as, let's say, pi 2 of x. Then, by rules of cosets, kung equal ang dalawang coset, that means that the elements satisfy this relation. Ito yung A inverse B is in H. No? Ito yun. Dati yan. AH, BH, if and only if A inverse B is in H. Parang ganyan. Kasi H is yun yung stabilizer ng X. So it means to say that this mapping will fix X in its place. If you apply pi 1 on the left, you will get Parang mali ito. No, yeah. If you apply pi 1 on the left, yung left-hand side mo magiging pi 2 of x, yung right-hand side mo magiging pi 1 of x. Biniligtad ko lang. Therefore, yung phi of pi 1 of h equals phi of pi 2 of h. Hence, the mapping phi that we have defined is really well defined. Reversing this argument, no, kung dito ka naman magsisimula, i-reverse yun na makakarating ka doon, will prove that phi is actually 1 to 1. And phi is obviously onto. Hence, phi is a bijection. So the number of elements in the G orbit is equal to the number of left cosets of H in G. That's K. That's the G orbit. And therefore, proving the orbit stabilizer theorem. Now, of course, we do not just stop there. The orbit stabilizer theorem is one of the most powerful tools in abstract algebra, as it is a good tool for counting objects, as you will see in the next few slides. Here we're going to talk about rotational symmetries in the three-dimensional space. Now, unlike a rotation in the plane, a rotation in the plane fixes a point. It's called the center of the rotation. A rotation in R3 fixes a line pointwise. What do I mean by that? A rotation in R3 has a fixed line. Ang ginagawa niya, parang umiikot ka around that line. Lahat ng mga points dito hindi gumagalaw at a certain angle. Ang tawag natin sa line na yun, we call that the axis of rotation. It can be defined by fixing a line as the axis and selecting an angle theta, yung amount ng rotation na gagawin nyo. Of course, may mga formulas available, but the explicit formula can be a little complicated. It uses a lot of trigonometric functions and matrices. As an example, I will show you an example. The rotation about the z-axis at an angle theta may be represented using the following matrix transformation. But this is a thing in geometry, Kaya sabi sa inyo, in general, paano pag yung axis of rotation pa ay slant, hindi z-axis, medyo mas mahirap yung itsura ng matrix mo. Tsaka paano kapag hindi tumadaan sa origin yung axis, ita-translate niya pa. Okay, so that's quite complicated. Kaya instead, we will define rotations by specifying a line and an angle instead. Huwag na nating pakita yung explicit na formula kung paano kinakalkula yung mga coordinates. Okay? Anyway, this is not a geometry subject. Parang ano lang ito. Application ng abstract algebra sa geometry. For a closed and bounded solid S in R3, the orientation-preserving symmetries of S are rotational symmetries. When you say symmetry, again, it fixes the solid S in its place. Yung mga isometries that fixes S in its place and fixes the orientation. When you say fixes the orientation, normally ang mga orientable surface kasi may outside, may inside, closed and bounded. May outside, may inside. Halimbawa yung surface ng sphere, meron siyang outside, merong inside. Pag sinabi orientation preserving, yung outside remains outside, inside remains inside. So the only symmetries that isometries that fixes this property are the rotational symmetries or the rotations in R3. Wala nang iba. Hindi kagaya sa wag na nga. Halimbawa ito, tingnan nyo yung pyramid na ito. Yung pyramid na ito ay may base na pentagon, regular pentagon actually. Kasi ito yung apex niya, Meron tong 5 rotational symmetries. And ano yung 5 na yun? Ito yung isa. I-rotate mo ng 72 degrees about this axis. 72 degrees. Tapos, pwede ka rin mag-rotate ng 72 degrees, 144 degrees, yun yung r squared. Yung r cube, tatlong 72 degrees. Yung r to the fourth, apat. Siyempre, yung limang 72 degrees, 360 degrees. Yun yung science ng 72 degrees. Dinivide ko kasi in 360 sa 5. At yung group na ito is a cyclic group of order 5, therefore isomorphic to Z sub 5. In general, pag meron kang pyramid na may regular n-gon na base, ang group of rotational symmetries niya ay Z sub n, cyclic. Okay? Can generalize. So, ang tawag natin sa kanila, kapag ganyan, no? We call it a polyhedron. A polyhedron is just a solid bounded by polygons as faces. Pag sinabing convex, pag nagkumuha ka ng dalawang points doon sa surface ng polyhedron, no? Ginawin mo yung straight line, yung line ay nasa loob pa rin ng polyhedron. Okay? Meron tayong Euler's theorem na tinatawag for polyhedra. Euler observed that actually he was able to prove that even though he was blind at an early age, no? He was able to prove that if you count the number of vertices, let's say that's V, and the number E of edges, number F of faces in a polyhedra, basta convex, no? According to him, there's a constant number that's equal to 2 and it equals V minus E plus F. Pag kinalculate mo ito, lagi raw yan magsasum up to 2. Yeah, isn't it nice? In fact, to those of you who were my students in modern geometry last semester, I think, 2 semesters ago, prove natin ito, no, using spherical geometry. Gumamit tayo ng spherical geometry to be able to prove the following theorem by Euler. But here, we will not be proving it. We will accept this as a fact. So, makikita nyo dito sa example na to, sa pyramid na may pentagon base, yung number of vertices ay 6, 5 doon sa pentagon, isa sa apex, 6. Meron siyang 10 edges, no? Ano yung 10 edges? Ito yung 1, 2, 3, 4, 5. 5 rin yung sides ng polygon, kaya 10. At yung number of faces, 1, 2, 3, 4, 5, 6. Pag kinalculate nyo nga naman talaga yung V minus E plus F, equal siya sa 2. Interesado tayo sa, hindi lang ba sa polyhedron. Gusto natin yung mga regular polyhedron because of its symmetric nature. Kasi nasa group theory tayo, no? A regular polyhedron is just a polyhedron whose faces are congruent regular polygons. Kapag, syempre, maraming polyhedron, no? Regular. Basahan ba, triangle lahat ng sides, mapa-convex, mapa-hindi, regular polyhedron. Pero kapag ang regular polyhedron mo, ginawa mong convex, bloated, walang dent, no? Ang tawag doon Platonic solids. And it was named after Plato because Plato was one of those who worked on discovering different types of solids that has this property. Inalam niya, no? And he discovered 5 Platonic solids in his time and wrote about them in a paper, no, called Timaeus around 360 BC. But of course, even before Plato, it was known to be, that the Pythagoreans and the Egyptians were already studying the solids or looking for the solids, and in fact, that's in a time even before Plato. Okay, and si Plato. It turned out na ito yung 5 Platonic solid na na-discover ni Plato. Yeah. Meron tayong tinatawag na yung mga Platonic solids are classified according to the number of faces. For example, ito yung number of faces dito ay 4. Ang mga faces mo ay regular triangles. When you say regular triangles, equilateral triangles. Kaya ang tawag dito ay tetrahedron. Regular tetrahedron. Ito naman regular. Ang faces mo ay 6. Hexahedron. Una nga tayong tamarin. Pero meron tong common name. Ang tawag nyo dito ay cube. Diba? Ito naman may 8 triangle na faces. Kaya ang tawag dito regular octahedron. Ito, ilang faces meron ito? Bilangin nyo nga. There should be 12 pentagon faces. Ang tawag dito regular dodecahedron. At yung pinakamalaki, yung number of faces ay may 20 faces. Lahat yan triangles. Ang tawag dyan regular icosahedron. Na-discover lahat ito ni Plato in his time. And only during the time of Euler, using his formula, yung V minus E plus F equals 2, gamit yung formula na yun, we were able to prove that there are only 5 Platonic solids. So, yung mga nahanap ni Plato na 5, actually, may proof na tayo na 5 lang talaga sila. Wala nang iba. Marami pang ibang regular polyhedron ha, pero 5 lang yung convex doon. Naintindihan nyo? You can Google kung ano pa yung iba. Kaya meron ka lang 5 Platonic solids. In the time of Plato, he associate every Platonic solid with the elements na air, earth, fire, cosmos, tsaka water. No? For him, he considered octahedron as the air elements, cube yung earth, tetrahedron, fire, dodecahedron, cosmos or the universe, icosahedron represents water. Saan nyo pa makikita ito, no? Halimbawa yung icosahedron, yung mga yung structure ng mga macrophages ba yun sa sa biology? Parang pag nag-drawing, ang itsura nila parang yan, tapos may paa silang parang scary na ganon. Ganyan, di ba? Icosahedron ang shape ng mga ulo nila kapag sinilip mo sa electron microscope kasi according kasi remember ang foundation ng biology ay let's say evolution, no? Isa sa mga proposal because of evolution. Ang evolution kasi parang nagmi-minimize or pinaka-efficient yun yung nag-evolve. Sa mga shapes kasi na ito, ang icosahedron daw ang may pinaka malaking volume that minimizes surface area. Kaya, syempre, to maximize the volume with minimal surface area, kailangan mo yung pinakamaraming faces. Kaya, gamit yung fact na yun, parang siguro natutunan ng due to evolutionary reasons, yun yung nag-evolve na shape ng mga ulo ng mga mga macrophages na yan. Kung ano man ang tawag sa kanila, I don't know. Now, ang mga polyhedron meron tinatawag na dual. The dual can be obtained by replacing each face by a vertex. Now, tapos i-connect mo yung dalawang vertices kung yung corresponding faces kung saan mo sila kinabit ay adjacent by an edge. Halimbawa, ito yung cube. Nakikita niyo yung cube? If you place one vertex to each of the faces of the cube, kagaya ng ganyan, tapos i-connect mo, halimbawa ito, i-connect ko sila kasi yung mga faces na to adjacent. Connect ko to, connect ko yun, connect ko sila, connect ko yun, no? And so on. Ang mabubuo ko ay octahedron. Kaya nga ang hexahedron, which is the cube, ang dual niya ay octahedron. In fact, ang dual ng octahedron ay hexahedron. So, parang complement yan. Kung dual ng hexahedron ng octahedron, ang dual ng octahedron ay hexahedron and vice versa. Kapag nilista mo yung mga duals ng mga solids, you will find that the tetrahedron is self-dual. Hexa and octa are duals, while dodeca and icosa are duals. And why talk about duality over here? Kasi kapag ang dalawang polyhedra ay duals, yung mga group of rotational symmetries nila ay actually isomorphic. So, in this case, dahil 5 yung solids natin, no, 3 na lang yung hanapin natin. Yung symmetry group nung tetra, nung hexa, tsaka dodeca. Kasi yung octa isomorphic lang naman pala sa hexa. Yung icosa isomorphic lang sa kung ano man yung group of symmetry nung dodeca. Let PFG be a Platonic solid with F faces such that each face has G sides. Ito na. Papasok na yung abstract algebra. Kunwari, F faces, G sides, bawat face. Okay? Halimbawa, yung regular tetrahedron. So, ano yung mga Platonic solids natin? Tetrahedron, P, 4, 3. Kasi, ano eh? Ano ba yun? Anyway. Pag hexa, P64. Bakit P64? 6 na cube. Octa. 8 triangle. P83 yun. Dodeca. Meron kang 12 na pentagon. Icosa. Meron tayong 20 na triangles. Ayan yung mga combinations ng F and G. Let G denote the group of symmetries of PFG. Then as you can see, lahat ng mga symmetries, rotational symmetries, it will permute the faces. Bawat ikot mo dun sa polyhedron natin, nagpe-permute lang yung mga faces. Goes from one face to another face. Tama ba ako? If you fix a particular face, no? If F is a face, then the G orbit of F is the entire set X. Kasi nga, let's say meron kang regular dodeca. Pare-parehas kasi yung mga faces and very symmetric ang nature nila. Pwede kang gumawa ng rotation so that yung isang face pupunta sa another face. So, yung isang face makakarating sa lahat. Hindi ko lang ma-drawing or hindi ko ma-illustrate by hand. Pero parang you get the idea. Kaya yung G orbit ng F ay kasing dami ng F, ng X, the elements ng X, which is the small f. Also, the stabilizer of F, ano naman yung stabilizer ng face? Ito yung mga rotations that fixes the face in its place. Ano lang yun? So, kunwari, meron kang pentagonal face, kunwari, regular dodeca. Ay, ganyan ang itsura ng regular dodeca, no? O, kunwari lang. I cannot draw this by, anyway. Kunwari, ito na isang face. Ano yung mga symmetries that fixes this in its place? Kunwari, 5 rotation lang. Yung identity, 72 degrees, di ba? 144 degrees, 216, tsaka 288. 5 lang. Kaya nga, actually, yung stabilizer ng F is a cyclic group generated by R. This is a rotation of order G, kung ilang yung number of sides, di ba? Yun yung order ng rotation na R. About the line through the center of F, and here therefore the number of elements in the stabilizer is the same as the number of sides in a face, which is G. Hence, by the orbit stabilizer theorem, the number of elements in the group of symmetries is just F times G. Oh, so that means to say that for a Platonic solid, the number of symmetries, then nalaman natin kung ilang symmetries, no? By just counting the number of faces and counting the number of sides in each face, multiply mo sila, just the total number of elements in the group of rotational symmetries. Okay? As an example, let's look at the regular tetrahedron. Since the tetrahedron has 4 equilateral triangle faces, then the regular tetrahedron has 12 symmetries. Ayan yun. Ganyan yung regular tetrahedron. We claim, no, na yung group na yun actually ay isomorphic sa A4. Naalala niyo A4? Yung mga even permutations on 1, 2, 3, 4. 12 nga yan. Kaya ko yun diniscuss dati kasi darating yung araw na to. Recall that A4, kung di nyo naalala, you can pause and go back. Yung A4 may 12 elements. Ito yung mga elements. It has the identity. It has 3 cycles of the following form. Meron siyang 8 order 3 elements. At meron siyang 3 products of disjoint 2 cycles na ang itsura ay A, B, C, D. Okay, 3 plus 8 plus 1, 12 nga naman. Nilista natin isa-isa yan before. So, we only need to associate. Ang kailangan natin gawin para mangyari ito, we only need to associate each one of these to a symmetry of, kasi alam na natin na 12 eh. Kung bawat isa dito ay magre-represent ng symmetry ng equilateral, ay ng regular tetrahedron, we're finished. We're done. Of course, yung identity, hindi na natin yun gagalawin. Kasi talaga naman, imagine nyo lang, yung nag-fix ng tetrahedron in its place, yun yung identity. Yung mga 8 3 cycles, let's say ABC, hindi naman talaga lagi ABC yan. Nagpapalit-palit yan eh. 1, 2, 3. Okay, 2, 3, 4, and so on. In general, ABC, ang gagawin mo lang, labelan mo ng ABC yung isang side, no? Tapos, i-rotate mo ng 120 degrees. But 120 degrees? Kasi 360 over 3. Yun yung nire-represent ng ABC. Kunin mo yung midpoint ng isang side through the other vertex. Yun yung axis. So, this is a threefold rotation. While, yung other class, yung ABCD, yung product ng disjoint two cycles, this is a half turn or 180 degrees. Bakit? Kasi pagpapalitin mo si AB, pagpapalitin mo si CD, so you have to rotate this 180 degrees. Okay? Kung titignan nyo pala yung projections na ito, tsaka nito, parang 90 degrees sila. What I mean to say, pag yung yung camera nyo nilagay nyo dito, kunwari ito yung camera. Ayan, camera nyo, no? Kung titignan nyo pa ganun, dito sa other side, parang naka 90 degrees sila. Okay? So, therefore, really, the group of symmetries of a tetrahedron is A4. Yan, that's the theorem. Ano naman kaya yung hexahedron? Or octahedron, in this case. 24 yan. But 24? Kasi ang ang face mo ay cube, so 4. Ilang faces meron? 6. 4 times 6, 24. Tama, ang S of 4 ay may 4 factorial elements. Ngayon, ang tanong ko, paano ko naman nalaman, sir, na S of 4? Ang representation natin, bale, ganito. Ito, kunwari yung cube, no? Labelan mo yung mga vertices ng isang face as 1, 2, 3, 4. Now, bawat vertex may opposite vertex, diba? Ito 4. Labelan mo rin yun ng 4. Ito 3. Labelan mo ng 3. 2. Lagay mo dun 2. Ito 1. Bawat rotation na ito is a permutation on 1, 2, 3, at 4. For example, magbibigay tayo ng arbitrary na permutation. Kunwari, I want the one that fixes, ano ba, 2, 1, 4, 3 na lang, para for simplicity. Nasaan dito yung axis nung permutation na ito? 1 and 2 will interchange, 3 and 4 will interchange. Where can I place the axis? I think, paano ba to? I think, saan ba natin lalagay? I cannot find kung saan ko dapat ilagay yung axis. So, pa dapat lagay yung axis? Parang ganyan ba? I don't know. So, 180 degrees. Pag ganito. 180 degrees. If I do it like that. Yan. Yeah. Yeah. That's it. And all the rest, no, 24, lahat yun, it can be represented by an axis of rotation for the cube. For the dodecahedron, medyo mahirap itong i-represent kasi mahirap i-drawing ang dodecahedron, but kaya nating bilangin actually. The dodecahedron has 12 faces. Each is a pentagon, so 12 times 5, 60. Ito talaga namang 60, di ba? 5 factorial over 2. That's really 60. And that's a sub 5. I will leave that to you as an exercise kung paano i-represent yung mga elements. Okay? Saan nyo ilalagay yung 1, 2, 3, 4, 5? Ang idea parang ganun din. Yung 1, 2, 3, 4, 5 lalagay nyo sa vertices ng isang pentagon. Tapos sa opposite na pentagon, opposite na vertex 1, ganun din. It turned out na kung titignan natin yung mga groups of rotations na finite on R3, 5 lang ang possibilities. Zn, nakakita na kayo kung paano nakakagawa ng Zn, di ba? Yung pyramid na may n-gon na base. May A4, ito yung sa tetrahedron, S4 hexahedron, A5 dodecahedron. Pero merong isang additional, yung D-sub, and yung dihedral. Ang tanong, paano mo marirealize yung dihedral na group? Ito. Gagawin mo parang 2 apex yung may dalawang apices. Apices? Ano bang plural ng apex? Apex. Anong plural na ito? I don't know. Can you find the plural form of apex? May dalawang apex yung solid natin. Parang pyramid na dalawa, baligtaran. Ito kasi maliban sa pwede mong i-rotate, pwede mo pang, ano pang pwede mong gawin? Pwede mo pang i-rotate ng, halimbawa, ito. Kunin mo tong axis na to. Pwede mo pang i-rotate ito ng 180 degrees. Mangyari, that's a mirror reflection of the pentagon. Kaya ito isomorphic sa D sub 5. Ano kaya nyo? May arca dito na 72 degrees. Ito kung tatawagin mong S. Yan. Siya yung group na ma-generate ng R at saka ng S. Alright? Alright, so that's it for this lesson. And see you in the next one.